Hello, and welcome to another lecture in the course. So we're going to start looking at linear fractional transformations. So this is, we're not gonna quite finish 1.4. Today we're gonna split it into two parts to make it more manageable. All right. So what is linear fractional transformation? Well, it's really an expression like this, or so it's a function of z, right? Where we require that AD is not equal to BC, right? So that's what we mean by linear fractional transformation. For short, we'll just say LFT. Sometimes these are called Mobius transformations. Now, this condition over here, that guarantees that the ratio over here does not simplify, right? Because if it simplified, we just get a constant. We don't want that. We don't want this guy to be constant, right? That's basically what we're trying to do, right? It also makes sure, by the way, if you look at the denominator, right? I mean, you cannot have both C and D equal to 0, right? So you cannot divide by 0 either, right? So because if both C and D are 0, then, well, this is not satisfied. All right, so now if C itself is 0, well, then, as we said, D is not 0, right? So without loss of generality, we could just make it 1, right? Because we can just simplify. And then really F is just this affine AZ plus B. Now, what we can do is we can then define, so using the Riemann sphere, right, we can define F at infinity to just be infinity, right? As we said that, that any non-constant, non-constant polynomial is going to be is going to go to infinity, and this is definitely non-constant. A cannot be 0, right? If A is 0 and C is 0, again, we're not satisfying this condition, right? So we just define F and infinity to be infinity in this case, if C was 0. On the other hand, if C is not 0, right, then this expression is defined, well, maybe not for all complex numbers. It's not defined when z is minus d over c, right? Because that's when I'll be dividing by 0 over here, right? But we can define this guy to be, well, we'll define it at this point when we would be getting basically, something over 0, right? So as we said last time, well, that should just go to infinity, right? So we'll define it to be infinity at that point. And we can also define, what it means when z goes to infinity, right? And, well, you just sort of you compute the limit as limit of this expression as z goes to infinity, and that's a over c, right? So the mapping takes Riemann sphere to itself, and it's bijective. For any any A, B, C, and D where this is true, it is bijective. It's not hard to show. It's 1-to-1 and onto with these definitions, of course, right? So not just this expression, right? And it's continuous. So it's also not too hard to prove, right? So that's an exercise. Now, any LFT, any linear fractional transformation, actually a composition of some simpler LFTs. So first, translations. So I can define an LFT which is just z plus a, right, for some constant a, right, for some complex number a, right? So we could do that, and we're going to call it t sub a. I can have so-called complex dilation. So if I have a complex number a, I don't want it to be 0 because otherwise it wouldn't be an LFT, right? It would be constant otherwise. And I can take a times z, right? So that's as a complex dilation. So we're going to write it as D sub A, right? Then we need one more. So with translations and complex dilations, at best you could get affine things. So you need to add the division in there. And actually, we just need this inversion guy here, right? So 1 over z. We just need 1 over z, right? And all of these, again, define LFTs, right? So I can define them, right? The translation is just something that takes infinity to infinity, and the complex dilation is something that takes infinity to infinity. Inversion flips 0 at infinity, right? It takes infinity to 0, 0 to infinity, right? Now, let's show that any LFT is really a composition of these three guys, right? So suppose that we have an LFT like this. Now, without loss of generality, we could assume that either C is 1 or C is 0, right? Those are the two cases, really. And so if C is 1, I really have this expression over here. Now, just a little bit of algebra gives me this. And, now if you sort of read through this, well, it's really this composition, right? So I first, let's show how I go through it. So I have this translation by D, so over here, right? Then I invert that, right? So I have 1 over Z plus D, right? And then I dilate that with B minus AD, which is not going to be 0 because this is an LFT, right? So C is 1, right? So this is precisely that condition that, the thing that's not supposed to be 0. So that gives me this, makes the numerator that constant, right? So now I have this expression over here, and then I just translate it by A to add the A, right? So, okay, so maybe a little bit of, a little complicated, but not too bad, right? So that guy is a composition. Now for C equals 0, when we really have just AZ plus B, yeah, that one's easy, right? I dilate by A, right? A is if this is an LFT, A can't be 0, so that's a valid dilation, and I translate by B, right? And I get AZ plus B, right? So any LFT can be realized by a composition of T, TA, dA, and I, right, for different constants, right? So you only really need to sort of worry about these three guys when you're proving something about LFTs, as long as you know how things behave under compositions, right? Now let's see what these guys do. So translation is easy, right? I mean, moves everything. It moves the entire complex plane in the direction of A, right? And fixes infinity, right? So that's easy geometrically. Complex dilation, maybe a little bit more complicated. So it's a normal Euclidean dilation, which is just rescaling, right? By the size of A, by the modules of A, but it also rotates. So you get both. The complex dilation is basically both rotation around the origin and scaling, right? So in standard Euclidean geometry, you would have those two guys, right? So now we can do it just by one, right? By complex dilation, right? And that's really, why you make it a different term, right? Instead of just saying dilation, because then you could think of the Euclidean dilation. All right. Oh, and by the way, that also fixes infinity because those A times Z, right? It's polynomial again. Now inversion. So inversion is a little bit harder. Now it's also related to the Euclidean inversion from plane geometry. It's basically an inversion across a circle, but the thing about the functions that we want to study, the holomorphic functions, and LFTs are going to be holomorphic. we don't want them to, well, we don't want them, they do not change orientation. They do not flip orientation. They need to preserve orientation. Now, standard Euclidean inversion would invert the orientation, would flip the orientation. So to get something that preserves orientation, you need to do two things that flip orientation. So the complex inversion, this 1 over z, what it does, it's the inversion across the unit circle, and then a conjugation, which is an inversion across the real line, right? And here's a picture of it, right? So you start with z, and you invert across the unit circle, which is really just, taking the size of z, right, and making this size of z 1 over that, right? And that gives you, a point over here. And that, if you think about it, what happens is, it's basically, it's supposed to have the same direction as z. It's just supposed to have the modulus is supposed to be 1 over, right? So if you do a little bit of, algebra, you find it's actually 1 over z bar, right? So that's the standard Euclidean inversion across the unit circle. And then you just do a complex conjugation, you get the complex inversion, right? So this is what the inversion does. It inverts across the circle, and then it inverts across the real line, right? So now, and this is a fun exercise, but it's also a very useful exercise in terms of the geometry. So if I have any LFT, it will take as a map, right? It takes sets to sets, right? I can push forward sets. So it takes any straight line or a circle, and it maps it into a straight line or a circle. I mean, it could take a circle to a straight line and a straight line to a circle, but it takes the set of straight lines and circles to the set of straight lines and circles, right? So it preserves this set, right? And you can actually, you could even think of as this being sort of bijective on this set. It's in the sense that you can actually take, maybe not bijective, but sort of, you can think of it. You probably think of making it a bijective map, but basically you can take, what I really mean is that you can take any straight line to any other straight line or circle. So any straight line or a circle to any other straight line or circle. So for example, you could take any circle or a straight line, and you can find linear fractional that takes that circle or a straight line, let's say, to the real line, right? And then you could even normalize some points on it, right? So because you can easily, you also have like some LFTs that, let's say, preserve the real line. If I have z plus 1, right, preserves the real line. It takes the real line to the real line. 3z preserves the real line. So you can also move some points. All right, so that's a nice, useful exercise. So that's just what I also said. It's another exercise actually in the book. So there are 2 exercises. Now, the thing to why do we have to throw in straight lines? Well, straight lines are circles. They're just circles through infinity, and the way to think of that is, well, if you think in terms of the Riemann sphere, right? All of these guys are going to be circles on the. If I think of the stereographic projection that we defined last time, where we were, showing, the Riemann sphere, and we actually did a identification with an actual sphere. That guy, if in that geometry, if I look at a straight line in C, that's actually going to be a circle on that sphere that goes through infinity, right? So that set is actually, if I think of that geometry on the Riemann sphere, those are just going to be circles, right? There's no way to do a really straight line on on the Riemann sphere. So, all right. So next time we're gonna talk a little bit more about linear fractional transformation. We're gonna look at linear fractional transformations as matrices, and really talk about the Riemann sphere as the complex projective space, where then you can think of linear fractional transformations as matrices if you do that, and that's why they're called sort of linear fractional transformation. They're actually linear transformation. There's really 2 by 2 matrices up to scaling. So we'll do that next time.